Welcome back. In this section, we're going to talk about right-angle trigonometry. So in this section, we're going to be introducing six trigonometric functions, and for all of these functions, they'll take in as their input an angle that's in a right-angle triangle, and as their output, they will give us some sort of ratio of the side lengths of that triangle. Now, anytime you're talking about a right angle triangle, you know that opposite that 90-degree angle, you have a side called the hypotenuse. The other parts that we have for this triangle, the other two sides, their names that we'll give to them depend on where the angle is. One side will be adjacent to the angle or next to that angle. So if we're thinking about this angle theta, then this side would be the side that's next to it or adjacent to it, and this side would be the side that's opposite to it. The side that's opposite and the side that's adjacent depends on which angle you're talking about. So if we talked about exactly the same triangle, but we're interested in the angle at the top, the hypotenuse would still remain the same, but now it would be the vertical side here that's my adjacent side, and the horizontal side that would be my opposite side. So something that will be important here will be little diagrams of right angle triangles, so we're clear which side is the side that we're interested in, which angle is the angle that we're interested in, because who is the opposite side and who is the adjacent side depends on which angle you're looking at. So we introduce these six functions, and for these six functions, as they're defined, the angle is somewhere between 0 and pi over 2 radians, or in other words, in terms of degrees, somewhere between 0 degrees and 90 degrees. So we'll be able to find our trig functions for any angle between 0 and 90, but that also means that at this point in our life, we won't be able to find trig values or values of trig functions for angles that are smaller or equal to 0 degrees or larger than or equal to 90 degrees. So right now, the question of what is even sine of 0 degrees, that will be a mystery. We're going to have to get some other techniques available to us before we'll be able to talk about that. Same thing with larger angles, something like what is cosine of 100 degrees, that will also have to wait. So we have our six functions, and the six functions, the names of them, sine, cosine, tangent, cosecant, secant, and cotangent. And as little short forms, sine, sin, cosine, cos, tangent, tan, cosecant, csc, secant, sec, and cotangent, cot. This is kind of a similar thing to when we were talking about logarithms. These are not logarithms at all, but in the same sense where I would say that when we were talking about a logarithm, how log base a was the name of our function and x was the input for that function. The same sort of thing is going on here. When I say sine theta, sine is the name of my function and theta is the thing that's going into that function. So for all of these functions, we have sine of theta, cosine of theta, tangent of theta, cosecant of theta, secant of theta, and cotangent of theta defined, and they're all defined in terms of our side lengths for these triangles. So for the sine of theta, it would be the opposite side over the hypotenuse, for example. One other little bit of naming here, you might have noticed as far as the names go, we have a sine and a cosine. We also have a tangent and a cotangent. We also have a secant and a cosecant, so it kind of appears that there's a sort of pairs going on here. And those pairs, we call those the cofunctions of the original functions. Cosine is the cofunction of sine, and cosecant is the cofunction of secant, and cotangent is the cofunction of tangent. We're going to see in a little bit that there is a relationship between those pairs of functions, between a function and its cofunction. We're also going to see that there's lots of other kinds of relationships between our trig functions. You might notice just from the way that I have my functions laid out here that I have them kind of in pairs also, that sine and cosecant are a pair. Notice that cosecant, as it's defined, it's the reciprocal of sine. Same thing with cosine and secant. Those are reciprocals of each other. Tangent and cotangent, those are reciprocals of each other. So one of the things that you'll see throughout this section of trigonometry, not just this section, the entire chapter, is that any trig function can be expressed in a variety of different ways. So for example, you could think about cosecant of theta as being hypotenuse divided by opposite, but you could also think of cosecant of theta as being the reciprocal of sine. And depending on what we're doing, these different ways of thinking about our functions might be easier to use than others. Other thing to notice here is that all of our trig functions can be written in terms of just sines and cosines. We know that secant is the reciprocal of cosine, and cosecant is the reciprocal of sine, but the other two functions, tangent and cotangent, those can also be expressed in terms of sines and cosines. Tangent of theta is sine of theta divided by cosine of theta, and since cotangent of theta is the reciprocal of that, then cotangent of theta should be cosine of theta divided by sine of theta. So, although there are 6 functions, in a sense, sine and cosine are really the very most important of the 6. If we really know sine and cosine well, then any other things that we have to do with secants and cosecants and tangents and cotangents we'll be able to do in terms of sines and cosines. Okay, so here we've got ourselves a nice little right triangle, and I want to find the exact values of all the trigonometric functions of that angle theta. So we have the one side missing from our triangle here would be the hypotenuse. And one thing that we know is by the Pythagorean theorem, you know that in a right triangle, that the hypotenuse squared should be equal to the other two sides squared and added together. So what we know is that the hypotenuse squared should be equal to 2 squared plus 4 squared, which is the same thing as 4 plus 16, or 20. And that means that our hypotenuse should just be the square root of 20, which in simplest terms, 2 root of 5. In case you're wondering here, when I solved this equation for the hypotenuse, I did not do plus or minus the square root. And the reason I didn't do plus or minus is because the hypotenuse is a length, and lengths have to be positive. So if it was any other kind of an equation that we were solving, if you were just solving x squared equals 20, there would be 2 solutions. But for the hypotenuse, since it has to be positive, there's only the one. Okay, so now that we have our hypotenuse, we're ready to find our values of all of our 6 trig functions. And so for this, we just need to know our 6 trig function definitions. Now, the nice thing again is that if you know the relationships between your trig functions, you don't really have to remember all 6. So for example, I know that sine of theta is opposite over hypotenuse, which is the same thing as if my angle is theta, the opposite side would measure 4. And the hypotenuse, we know what it is. It's 2 root of 5. So that means sine of theta should be 4 over 2 root of 5. And then I'm just going to put this in simplest terms. The 4 and the 2 I can cancel. And then multiplying top and bottom by root of 5, rationalizing that denominator. There we go. I have sine of theta is 2 root 5 over 5. Now, where I'm going to get a second thing for the price of one, which is once I know sine of theta, I automatically will know what cosecant of theta is. Because remember, cosecant of theta should be the reciprocal of sine. And so if I remember that, I can say, well, cosecant of theta should be either, I could say, reciprocal of this, or actually more usefully, I could say it's the reciprocal of this. Reciprocal of 2 over root 5 would be root 5 over 2. And there we go. That is in simplest terms. I chose to use this one because once I took the reciprocal, it was already in simplest terms. If, on the other hand, I had chosen to look at this one and said, well, it's 5 over 2 root of 5, I would need to put it in simplest terms still. And that would only lead me to that answer, which I've already found. So, thinking strategically here, I was able to find cosecant theta right after I found sine of theta. And I'm going to do this same thing for cosine of theta. I know that that's adjacent over the hypotenuse. And for theta, the adjacent side measures 2. And so now, just to simplify, again, rewriting this in simplest terms, 1 over root 5 could be rewritten as root 5 over 5, multiplying top and bottom by root 5. And then there we go. We have our value for cosine of theta. And then similarly, we know that secant of theta, that's the reciprocal of cosine. And so we know since cosine is 1 over root 5, then the reciprocal should be root 5 over 1, which is the same thing as root of 5. So we've got now 4 out of our 6 trig functions. The last two, we have tangent of theta. Tangent is opposite over adjacent. Here the opposite side measures 4 and the adjacent side measures 2. So tangent of theta is 2. And cotangent of theta is our reciprocal of tangent of theta. So that should be then 1/2. One thing I want to just make sure that we're all aware of is that for the most part, and this is kind of a running theme for this class, we're interested in exact values only. So although you might have looked at your calculator and noticed that yes, indeed, there are trig functions on that calculator, I'm not really interested in finding out what my calculator tells me because my calculator is going to give me only decimal answers. What I'd like to know would be the exact values of these trig functions. And one thing to note is, for example, 2 root 5 over 5, that's not a number that can be written with decimals without rounding. If you tried to put that as a decimal, you'd have to round it, which means that if you wrote it as a decimal, you would not be giving me the exact values. So this is something where, although there is some calculator work for this section, a lot of what we'll be doing will be finding exact values, and that we'll have to do ourselves. So there we go. We've got our 6 trig functions. The other thing to notice here, of course, is that anything involving roots, which show up quite a bit, courtesy of the Pythagorean theorem, anything involving roots have to be written in simplest terms, and that means, of course, making sure that all denominators are rationalized. So I wouldn't leave sine of theta, for example, as 2 over root 5, because that wouldn't be in simplest terms. I would need to leave my answer as 2 root 5 over 5. All right, so here we've got ourselves a word problem. In a right triangle with angle theta, we know that sine of theta is 2/7. We don't have any sort of a diagram happening here, so this might be a good idea. We might want to draw ourselves a right triangle. And I'll put my angle theta somewhere. There we go. I've chosen that angle, that corner to be angle theta. And when we're defining when we're creating our triangle, we're going to use the fact that we know that sine of theta is 2/7, and that sine of theta is opposite over hypotenuse. So we know that the opposite side over the hypotenuse should be 2/7. So from that, we can say, well, why not have the opposite side measure 2 and have the hypotenuse measure 7? So for my angle theta, the opposite side, I'll have it measure 2, and the hypotenuse, I'll have it measure 7. And then that just means I have now only one side to find on this triangle, and that would be the adjacent side. And this is where, again, we're going to use our Pythagorean theorem. We know that the hypotenuse squared is the other two sides squared and added. So 49 is equal to 4 plus the adjacent side squared. So the adjacent side squared is 45. And so that means the adjacent side should be square root of 45. And in simplest terms, square root of 45, that's root 9 times 5, or root of 9 times root of 5. So 3 root of 5. There we go. So we've got now our value for the adjacent side, and since we know all three sides for this triangle, we can find all 6 trig functions. We already had sine given to us. Sine of theta was 2/7. And so that means we already, in a sense, have cosecant given to us, since that's just the reciprocal of sine. So that should be 7/2. So although there are 6 trig functions, really we only have 4 that we're going to need to find by ourselves, since we were given one and then the other one came kind of automatically. So we have sine and cosecant already done. Let's do cosine next. Cosine of theta, that's the adjacent side over the hypotenuse. And the adjacent side measures 3 root of 5, and the hypotenuse is 7. And that's already in simplest terms. That can't be simplified any further. Denominator is rationalized, so that's good for us. Secant of theta should be the reciprocal of cosine. That should be 7 over 3 root of 5. And that's not in simplest terms, so I will need to multiply top and bottom by root of 5 to give me 7 root of 5 over 15. And there we go. That's secant of theta. And then let's do tangent. Tangent of theta is opposite over the adjacent, which is the opposite side measures 2, and the adjacent side measures 3 root of 5. And to put this in simplest terms, multiplying top and bottom by root of 5, that gives me 2 root of 5 over 15. And then finally, cotangent of theta, that should be the reciprocal of tangent. Since tangent was 2 over 3 root of 5, then cotangent should be the reciprocal of that, 3 root 5 over 2. Probably not a big surprise that there are going to be some things that will flow from the Pythagorean theorem here, because the Pythagorean theorem is part of right triangles, and so if we're dealing with right triangle trigonometry, then that means there's probably going to be some identities that have to do with the Pythagorean theorem. And we do indeed. There are 3 identities. There are 3 relationships between our trig functions. One little bit of notation, though, before we go further, and that would be this. When we're talking about taking a trig function and squaring it, if you were to write something like sine of theta squared, in this case, the squaring would just be the angle. The angle is being squared and then put inside our trig function. So if you wanted to make it clear that it was the entire trig function being squared, you would have to put brackets around it. And then it would be clear to the reader that the angle went into the trig function and then the entire trig function got squared. One of the conventions that we have for notation is that to get away from having to use those brackets, if we want to talk about a trig function being squared or raised to a power, we put the square or whatever the power is right by that trig function. So when you see something like sine squared theta, what it really means is sine theta, the whole thing has been squared. And same thing with any other power. Sine of cubed theta, that would be sine theta, the whole thing cubed. And similarly with any other trig function that we have. So these identities are telling us that for whatever angle we're interested in, if you look at sine theta and square it, take the same angle, cosine theta, and then square it, those two things will always add up to 1, no matter what the angle is. And we have similar relationships between cotangent and cosecant, and also between tangent and secant. And all of this begins with our right triangle. So if we're thinking about our right triangle that we have, and I'm going to have this as part of my proof here, I'm drawing myself a nice little right triangle. And for this right triangle, we would have the angle theta that I'll put in it, which means that this side would be the opposite side, and this side would be the adjacent side, and this side would be the hypotenuse. Okay, so the fact that we know is by the Pythagorean theorem, you know that the hypotenuse squared is equal to the opposite squared plus the adjacent squared. And so now what I'm going to do to get these three identities is I'm going to modify this equation that I have so that it's expressed in terms of sines and cosines, or in terms of cotangents and cosecants, or in terms of tangents and secants. So to begin with, I'm going to take this equation and divide everybody by hypotenuse squared. And one thing cleans up really nicely, which is on the right side, hypotenuse squared divided by hypotenuse squared. No matter what the hypotenuse is, that should be 1. On the left side, opposite divided by hypotenuse, that would be sine of theta. So if you have opposite squared over hypotenuse squared, then you've got a sine theta times another sine theta. That first term is sine squared theta. Similarly, that second term, adjacent over hypotenuse, would be cosine of theta. And so if you have adjacent squared over hypotenuse squared, that should be cosine of theta whole thing squared, which we write as cosine squared theta. So there we go. We have our first trig identity proven. We know now, we can be happy and confirmed that sine squared theta plus cosine squared theta is equal to 1. Now the other nice part is the other two identities we can think of as flowing from this identity. If you know that sine squared theta plus cos squared theta is equal to 1, and if you remember that those other 4 trig functions can be written in terms of sines and cosines, then you have the idea for the rest of the proof. If I were to take this equation that I have and divide everybody by cosine squared theta, then on the right side, I've got the reciprocal of cosine that's been squared. You know that 1 over cosine of theta is secant, so 1 over cosine squared, that should be secant squared theta. Cosine squared over cosine, that should be 1. Sine over cosine is tangent, so sine squared over cosine squared, that should be tangent squared theta. And the third identity that we have also flows from sine squared plus cos squared is equal to 1. If we just divide everybody, instead of dividing everybody by cosine squared, this time we'll divide everybody by sine squared theta. And so what we have, 1 over sine squared theta on the right side, 1 over sine, that's cosecant of theta. So 1 over sine squared theta, that would be cosecant squared theta. On the left side, sine squared over sine squared, that would be 1. Cosine over sine, that's the cotangent function. So cosine squared over sine squared, that would be cotangent squared theta. And so there we go. We have our 3 trig identities. This gives us one extra tool to use if we're looking at evaluating a trig function exactly. If you're thinking about, for example, finding the value of sine of theta, if you knew the value of cosine of theta, then you could use sine squared theta plus cos squared theta equals 1 to solve that problem. Or if you knew the value of tangent, then you could use the third identity to find the value of secant. So depending on what we're looking to find and depending on what we know, we might have some other identities that could be useful rather than just thinking about things in terms of opposites and adjacents and hypotenuses. So for this example here, we've got an angle theta in a right triangle, and we know that sine of theta is 2/5. And all we want to do is find the value of cosine of theta. Now, we could do this the way that we did the previous problem, which is to draw ourselves a right triangle, to say that sine of theta should be opposite over hypotenuse. We could do some work and find out what the adjacent side is, and then once we know what that is, cosine is adjacent over hypotenuse. We could do things that way. Or we could use the fact that we know that sine squared theta plus cosine squared theta is equal to 1. And we know what sine of theta is. That's 2/5. So 2/5 squared plus cosine squared theta is equal to 1. And so now we really just have an equation to solve. And I'm just going to bring that 4/25 to the other side. 1 minus 4/25 is 21/25. And now if I want cosine of theta, I have that it should be square root of 21 over 25, which is root of 21 over root of 25, which is just 5. Now, you might be wondering, again, since we were looking at solving an equation with a square in it, should it be plus or minus square root? And in this case, the answer is it would have to be the positive square root. And the reason being, remember that for right triangle trigonometry, which is what we're talking about now, our angles are in a right triangle, cosine is defined as the adjacent side divided by the hypotenuse. And both of those are positive numbers, which means cosine has to be positive. This is something that we're going to see will change when we no longer talk about angles in a right triangle. When we make things more general and talk about trigonometry for angles in standard position, we'll see that actually there will be the possibility for our trig functions to be negative in those cases. But for right triangle trig, our trig functions are always positive. And that's why I didn't have to have plus or minus, because I knew it must be plus. It would have to be positive root 21 over 5. The last part that we have to talk about here is the relationship between cofunctions. Remember that we had pairs of functions, sine and cosine. We had secant and cosecant. There was tangent and cotangent. And I had said earlier that there was a relationship between those pairs of functions, and that is this, the complementary angle theorem. When two angles are complementary, they add up to 90 degrees. And one fun fact that you know, for a right triangle, since the three angles together have to add up to 180 degrees, then if you have a right triangle, if one of the angles is 90, then the other two angles have to add up to 90 degrees. So in other words, if we're talking about a right triangle, the other two angles, except for the right angle, those two angles will be complementary. And a fun fact here for the complementary angle theorem, it tells us that cofunctions of complementary angles, that they must be equal. So if you're looking at this first little diagram I have up top, sine of alpha and cosine of beta, that those should be equal because sine and cosine are cofunctions and that alpha and beta are complementary angles. That would be also true for secant of theta, secant of alpha and cosecant of beta, or tangent of alpha and cotangent of beta. Any cofunctions of complementary angles would have to be equal. And the reason for this, if you're looking for a quick proof, it just comes right from our diagram. Sine of alpha is opposite over hypotenuse, and that would be, in this case, b over hypotenuse. Cosine of beta would be the adjacent over hypotenuse, and for beta, the adjacent side is b. So you can see that sine of alpha and cos of beta must be equal. Similarly, you can say other kinds of related things about secant of alpha and cosecant of beta. You know that secant of alpha should be the reciprocal of cosine. Cosine of alpha would be a over hypotenuse, so secant of alpha should be hypotenuse over a. And cosecant of alpha, cosecant of beta should be the reciprocal of sine. Sine is opposite over hypotenuse, and so for cosecant, it should be the reciprocal, in this case, hypotenuse over a. And you can see here, secant and cosecant, secant of alpha, cosecant of beta, that they're equal to each other. And you can say similar things about tangent and cotangent. Tangent of alpha should be opposite over adjacent, and for alpha, opposite is b, adjacent is a. For cotangent of beta, that should be adjacent over opposite, and for beta, the adjacent side is b, and the opposite side is a. So there we go. We can feel confident in our complementary angle theorem. And that means for things like this, we actually can evaluate these even though we don't know yet how to find cos of pi over 3 or sine of pi over 6. The reason we can evaluate them is, if you're thinking in terms of degrees, pi over 3 radians is the same thing as 60 degrees, and that pi over 6 radians, that's the same thing as 30 degrees. So these definitely are complementary angles of each other. They add up to 90 degrees. And so that means that cosine of 60 degrees should be the same thing as sine of 30 degrees. So that means this cosine of pi over 3 minus sine of pi over 6, since they're both equal to each other, one thing minus the other should be equal to 0. And similarly for the second question, for b, we have cosecant of 75 over secant of 15, and these two angles do add up to 90 degrees, and these are cofunctions, secant and cosecant. So you know that cosecant of 75 is the same thing as secant of 15 degrees. So cosecant of 75 degrees divided by secant of 15 is the same thing as secant of 15 over secant of 15, which is 1.